Dear all, a very good day. Now we are going to start unit 2, which is based basically upon the MOS inverter characteristics. In this video we are going to see different type of MOS inverters, how we see their working, their output characteristics, on what factors their output characteristic depends, different voltage levels which are very important for their calculation, then their noise margin. The basic type of MOS inverters that we are going to see are resistive load inverters, then NMOS load inverter, and the most important one is CMOS inverter. Okay, we will be looking at the characteristics, why and how they differ from the ideal inverter characteristics, their power and area consideration, and calculation of various voltages required for understanding their characteristics. Okay, so before going to all that stuff, let us first see what is an inverter and a static characteristic. Okay, so we all know inverter is one of the first basic gates that we learn about. We have seen that it has got a single input and a single output. Whatever we give in the input, output is complement of that input form. So if A is the input, then output B will be equal to A bar. Okay, the inverter is the most fundamental logic gate that performs Boolean operation on a single input variable. So we will examine the DC characteristics of various MOS inverter circuits. The logic symbol and the truth table of an ideal inverter are shown. In the MOS circuit, both the input variable A and the output variable B are represented by node voltages represented to the ground potential. Okay, so here it is a basic symbol of an inverter which has got an input A. This is the symbol of inverter, and then we have got an output B which is equal to A bar. Here is a simplified truth table of the inverter which shows when A is equal to 0, B is equal to 1, that is complement of A, and again when A is equal to 1, B is equal to 0, that is complemented form of A. Now these voltages are for the logical levels 0 and 1 are standard voltages. If we are using a normal positive logic, then we will understand that a logic 0 is represented by 0 volts, whereas a logic 1 is normally represented by 5 volts or 12 volt and so on. Okay, so using the positive logic convention, the Boolean or the logic values of 1 can be represented by a high voltage of VDD, and the Boolean logic value of 0 volt can be represented by a low voltage 0. The DC voltage transfer characteristic of an ideal inverter is shown alongside. Okay, so if we will look, this is how a DC voltage characteristic of an inverter looks like. Here on the y-axis we have taken Vout, that is the output voltage, whereas on the x-axis we have taken Vin, that is input voltage. The maximum swing for both output voltage and input voltage is still VDD, that is voltage high levels. Okay, now if we will be looking at this characteristics, now if we will look at the center of this characteristic, there is a voltage level mark VDD by 2. Normally this voltage level is called the inverter's threshold voltage, VTH. For any voltage between 0 to VTH, that is VDD by 2, from here 0 to VDD by 2, that is VDD by 2 is here VTH. Okay, the output voltage Vout is equal to VDD, that is logic 1 level. Now output switches from VDD to 0 when input is equal to VTH. Now we are seeing that input here is equal to VTH, So there is a steep drop in the output voltage, and now it has shifted from from VDD to 0 volts. Okay, then the output switches from VDD to 0 volt when input is equal to VTH. For any input voltage between VTH and VDD, the output voltage assumes a value of 0 logic. Okay, for any voltage level between VDD by 2, that is VTH, to VDD, output will be 0 volts. Okay, then thus an input voltage of 0 to VTH, okay, is interpreted by an ideal inverter as logic 0, while the input voltage from VTH to VDD is interpreted as logic 1. Okay, so from 0 to VDD by 2, input voltage is logic 0, and from VDD by 2 to VDD, input voltage is assumed to be logic 1. The DC characteristic of an ideal inverter will obviously differ from in various degrees from an ideal characteristics. So if we will be comparing the characteristics of an ideal inverter to the characteristics of a real inverter, they will not be same. Okay, so here was a discussion until that we were discussing about. Okay, using the positive logic convention, the Boolean or logic value 1 can be represented by a high voltage of VDD, and the Boolean logic of 0 can be represented by a low voltage 0 volt. The DC voltage transfer characteristic of an ideal inverter is shown alongside. The voltage VTH is called inverter threshold voltage. Note that for any input voltage between 0 and VTH, it is VDD by 2, the output voltage is equal to VDD logic 1. The output voltage switches from VDD to 0 volt when the input is VTH equal to VTH. For any input voltage between VTH and VDD, the output voltage assumes a value of 0 logic 0. Thus input voltage between 0 and VTH is interpreted by this ideal inverter as logic 0, while an input voltage between VTH and VDD is interpreted as logic 1. Now, the DC characteristics of an ideal inverter will obviously differ in various degrees from an ideal characteristics. Okay, so if we are looking at an actual inverter, it will not show this steep transition between 0 and VDD. There will be some changes. Okay, the accurate estimation and manipulation of the shape of the VTC for various inverter types are actually important part of the design process, and the characteristics that we get from an actual inverter are very important to understand the designing of an inverter process. So next figure will show a generalized circuit structure of an NMOS inverter. Okay, this is the figure which is showing a generalized structure of an NMOS inverter. Okay, the input voltage of an inverter circuit is also the gate to source voltage of an NMOS transistor. So this is an NMOS transistor, and its gate voltage, that is whatever voltage is applied to its gate, is the input voltage for the present circuit, and this voltage is known as gate to source voltage because source is grounded terminal. Okay, therefore the input voltage of an inverter circuit is also the gate to source of the NMOS transistor. Okay, Vin is equal to VGS, while the output voltage of the circuit is equal to drain to source voltage. Okay, and output voltage of this circuit this is the drain terminal of our NMOS, this is the source terminal, the output is connected between drain and source terminal, so output voltage is Vout, that is equal to VDS. Now the source to substrate voltage, very important. This is the substrate part because we are using the 4 terminal symbol of MOSFET. So the source to substrate terminal of an NMOS transistor is called the driver transistor. Okay, This NMOS transistor is called a driver transistor, and its source to substrate voltage is grounded. Hence, source to substrate potential will be 0 volts. In this generalized representation, the load device is represented as a two-terminal circuit. Now, this is the load device. This may be a resistor. This may be depletion mode NMOS. This may be PMOS. So, this device here is shown in a very generalized form. Okay, is represented as a two-terminal device. We are just showing two terminals here. The current from this load device is IL, and voltage across this device is VL, as shown here. Now, one terminal of the load device is connected to the drain channel of the NMOS transistor. So this load device is connected to the drain of the NMOS transistor at one part, and at the other end there will be a supply voltage for this transistor. The output terminal of the inverter is shown above is connected to the input of another MOS terminal. Now, this is the output terminal of the inverter, and it has been connected to the other device. It may be another MOS inverter or any other MOSFET device. Therefore, the other device is represented by this lumped capacitance in the circuit. Okay, and is called as Cout. Since the DC current of an MOSFET transistor is negligible for all practical purposes, there will be no current flow in and out of the input and output terminals of the inverter in DC steady state. Okay, so no current will flow in this device in DC steady state, as its current gate current is negligible. Okay. Next time we will look at the voltage transfer characteristics of this inverter. Thank you.